Okay, for this review video, we're going to look at this first sets here, A, B, C, and D, and first convert these using set builder notation. First off, A, these are all integers, so I can write this as the set of all integers such that n is between 7 and 11. So that's one way of doing it. If you had natural numbers here, that's fine. If you put z plus here, that's fine. If you had 6 is less than n, less than 12, as opposed to less than or equals, that's also fine. There's not one unique way to do these. Some make more sense than others, but certainly there's plenty of ways to logically write this in set builder notation. Next we have multiples of 3 up to 15. And so here I have natural numbers, positive numbers, such that 3 divides n, and also n has to be less than or equal to 15. So that's the way that I would do this. You could also have n less than 16 or n less than 17. That would also work. I'm not sure why you'd want to do that, but it certainly would produce the same set B. Next, we have this set C here. So here we'll have natural numbers. Now I'm going to switch letters just for the sake of diversity. The dummy index doesn't matter. So we'll have integers k such that, or so positive integers, such that k is less than or equal to 20 and k is prime. So these are all of the numbers that are less than or equal to 20, which are prime. And lastly, D is the set 10 and 20. This isn't very descriptive, so there's plenty of ways this could be done. The way that I chose to do this was to say these are the numbers that are positive integers, such that j is less than or equal to 20, and 10 divides j. There are other ways that this could be done fairly creatively. That's the one that I chose. All right, let me add a few extra questions that were not in the original statement, but are in the video that you have now. Let's describe the set E, 2, 4, 8, 16, 32, 64, and 128, and so on. There's a couple ways that this can be done. One way would be to say that this is the set of all n that are integers, such that n is equal to 2 to the k for some positive integer k. So this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And so this is the set of all n such that n is equal to 2 to the k. Now this could be written more succinctly as just simply 2 to the k, where k is some integer n, or some integer in the natural numbers. So that would, both of these, either one, would be perfectly acceptable ways of writing the set E in set builder notation. For the set F, we're looking at now the interval from 0 to 5. Now, even though there are no curly braces here, that is a set. It's a set of all numbers that are in this interval from 0 to 5, counting the endpoint at 0, but not counting the endpoint at 5. So this can be written as the set of all real numbers, such that x is at least equal to 0, but is strictly less than 5. So I've got a bracket here, so that's the less than or equals, and I have the open parentheses here, so that's the less than. And I could have double brackets or double parentheses or parentheses then bracket, and I would have a similar looking set builder notation. Last one for the set G, this is everything that is less than or equal to 2. So to the left I can go to negative infinity. To the right I'm bounded above by 2. So this would be the set of all real numbers such that x is less than or equal to 2. And clearly I will not ever have a bracket on negative infinity because x cannot actually equal negative infinity. So that's the sets E, F, and G. So don't forget about doing interval notation, and also it is acceptable to have something like this where I have a function here and then the right side says the properties of the variable here. Okay, so with that we'll recontinue the video with the solution of problem 3.22. Okay, now let's take a look at these sets down here and figure out what all of these are based on the definitions here. First, the power set of D. D has 2 elements, and so the power set will have 2 to the 2 or 4 elements. So this is equal to empty set. Excuse me. The set containing 10, the set containing 20, and the set containing 10 and 20. So that's the power set for D. A union D. Okay, A union D would be 7, 8, 9, 10, 11, 10, 20. Now, to avoid making it look like it has 7 elements, I'm not going to list the 10 twice. So 7, 8, 9, 10, 11. I've already listed 10 once, and so I don't list it a second time, 20. Now, there would be nothing quote-unquote wrong with listing out 10 twice. It would be the same set, but it certainly looks better to not repeat elements. A intersect D. A intersect D is the set of everything that's in both A and D. And as we just saw, 10 is common to both, and that's it. And so A intersect D is the set containing 10. Notice it's not the number 10, it's the set that contains 10. All right, A cross D, A times D, the Cartesian product of A and D. All right, this is going to have 10 ordered pairs. So A has 5 elements, D has 2 elements, and so this will have 5 ordered pairs. So this means the first part comes from A, and the second part comes from D. So 7, 10, 8, 10, 9, 10, 10, 10, and 11, 10. So that's the first 5 ordered pairs. Then the next ordered pairs with 20 as the second value. 720, 820, 920, 1020, and 1120. And so this set of 10 ordered pairs would be the Cartesian product A cross D. D cross A, well, it's going to look an awful lot like this, except that the roles will be reversed. The first number comes from D, and the second number comes from A. So 10, 7, 27, that's the first 2. Then 10, 8, 28. 10, 9, 29. 10, 10, 20, 10. And then finally 10, 11, 20, 11. And so that would be the Cartesian product D cross A. It would have been perfectly acceptable just to flip these 10, 7, 10, 8, 10, 9, 10, 10, 10, 11, and I would produce the exact same list that's written out here, just in a different order, and as we've already established, the order does not matter. Okay, number 6. A intersect B union D. So this says figure out A intersect B first. A intersect B, 9 is common to both lists, and that's it. So 9 union D, 10, 20. And so that's going to be just simply 9, 10, and 20, this set with 3 elements. Okay, this one says A union D intersect B union D. Okay, so A union D, we just did it here. 7, 8, 9, 10, 11, 20. Intersect. Then B union D, if I take the union of B and D, I see that nothing is common to B and D, so I can just simply list out all 7 things. 3, 6, 9, 10, 12, 15, and 20. And they don't have to be listed in order, but certainly it makes it easier to read if they're listed in order. Now I take the intersection of this set and this set. So let's see, what's common? 9 is common to both, 10 is common to both, and 20 is common to both. So this is 9, 10, and 20. And this is actually one of the theorems from class. Not surprisingly, these 2 things are the same. And it turns out that in general, union distributes over intersection. And so A intersect B, whole thing union D is equal to what you see here on line 7. Okay, B minus C. So this means everything that's in B but not in C. So what's in B but not in C? Well, 3 is in C, so I don't want to list that, but all these other things are not in C. So 6, 9, 12, 15. Those are the things that are in B but not in C. C minus B. What's in here that's in B? Well, 3, and that's it. So C minus B would be equal to 2, 5, 7, 11, 13, 17, 19, and that's it. So this is the list of things that are in C but not in B. Okay, number 10. If the universal set is all the integers, positive integers 1 through 20, find A complement intersect B complement intersect C complement intersect D complement. Okay, so this one's going to take a little bit of work, so let me do it down here. Okay, so A complement. And let me write down what the original set was. 7, 8, 9, 10, 11 complement. The universal set are all the integers from 1 to 20, and so I would write this out as 1, 2, 3, 4, 5, 6, and then 8, 9, 10, 11, or sorry, 8, 9, I'm sorry, I blew it. 7, 8, 9, and 10, and 11 aren't in, so 12, 13, 14, 15, 16, 17, 18, 19, and 20. All the numbers from 1 to 20 except for 7, 8, 9, 10, and 11. B complement. Now, B was 3, 6, 9, 12, and 15. So I want the complement of this. And so that's equal to 1, 2, not 3, 4, 5, but not 6, 7, 8, but not 9, 10, 11, but not 12, 13, 14, but not 15, and then everything else up until 20. C complement. Now C were all the prime numbers up to 20. And so the complement will be 1 and then all the composite numbers. 4, 6, then everything between 7 and 11, so 8, 9, 10. 12, then between 13 and 17 we have 14, 15, 16, and then 18 and 20. And then finally D complement. D was only 10 and 20. And so that'll be everything except for 10 and 20. So it'll take me a while to write this out, but everything except for 10 and 20. That's between 1 and 20. Okay, so those are the 5 sets. Now, the question asks for A complement, intersect B complement, intersect C complement, intersect D complement. So let's go through these and see what's in all sets. 1 is in all the sets. 2 is not in C, so I don't list that. 3 is not in C, so I don't list that. 4 is in all the sets. Five is not in C complement. 6 is not in B complement. 7 through 11 I don't have to worry about. 12 is not in B complement. 13 is not in C complement. 14 is common to all 4. 15 is not in B complement. 16 looks like it's in all 4. 17 is not in C complement. 18 is common to all 4. 19 is not in C complement. And 20 is not in D complement. Shouldn't list that. And so the intersection has these 5 elements. Okay, now number 11, find this. So let's figure out A union B union C union D complement. All right, so here are the numbers. So let's see. 2's in there, 3's in at least one of them, 4's not anywhere, 5 is in at least one of them, 6 is in at least one of them, 7 through 11 are in at least one of them, 12 is in at least one of them, 13 is in at least one, 14 is not to be found, 15 is in at least one, 16 is not to be found, 17 is here, 18 is not to be found, 19 is there, and 20 is there, and I want the complement of this. So everything from 1 to 20 that isn't there. So 1's not there, 3, 4's not there, 6, 7, 8, 9, 10, 11, 12, 13, 14's not there, 16 is not there, and 18 is not there. And not surprisingly, these two things are the same by De Morgan's laws. So that was a brute force way of confirming De Morgan's law that these two things are in fact always equal to each other. And just this problem illustrated that.